Hi, everyone. I'm really excited to tell you guys a bit about what I've been working on. So earlier we had some great radio talks. Adele was focusing on the early emissions, so the first couple months was like where you start looking for that emission. I'm going to talk about a couple years later is what I mean when I'm talking about delayed radio emission from TDEs. Just very quickly though, so I'm in a period of transition. I'm going to start at the University of Oregon as a professor this fall, and I'm building a research group there, going to be listing a postdoc this fall. So if this sounds cool to you and you're interested, come talk to me later. So late time emission. Most initial radio TDE searches, as we were saying, occur within the first 1 to 2 months traditionally, I would say, for radio TDEs. And about 20% of TDEs will be detected at that time. What has happened in previous years in the field, though, because radio telescope time is precious, when things were not seen, people went and looked at other things. Recently, though, there were 2 radio TDEs, Assassin 15OI and IPTF 16FNL, which became radio bright over 100 days after the initial TDE event happened. So no radio emission, then detected after 100 days. So then you could ask yourself, is this common? Are we overlooking something in the radio TDE population that we haven't been looking at before? So to answer this, what our collaboration did is we did a campaign with the VLA and with Meerkat of about 30 older TDEs, so 2 to 3 years old, that had no prior radio emission associated with them. And I'm going to focus a bit about what this sample showed us in this entire thing. So the first one I'm going to start with, Adele was talking also like everybody has a favorite or favorite TDE. This is definitely mine, AT 2018 HYZ. And the reason is to set the stage here. So if we have the jetted TDE up here, Swift J1644 plus 57, here we have a more typical TDE that had prompt radio emission detected, AT 2019 DSG. Here we have Assassin 15OI, which we're going to hear a lot more about in our next talk, so I won't go into great detail. I'll just point out, though, for those who don't do radio normally, we're talking 3 sigma upper limits with those triangles there on our noise. And then here we have IPTF 16FNL. Now I'm going to add another TDE into the mix, AT 2018 HYZ. And it's doing something that we haven't really seen before, which, so if you look at it, we have several upper limits that were pretty constraining. The last upper limit was about 9 months before its initial detection in June 2021, so about 982 days after the first optical detection of the TDE. For the record, I'm just going to talk about things in terms of the date after first optical detection. Obviously, that's not perfect, but when you're talking hundreds of days after, I think you're allowed to get away with a few days there. And it was rising as fast as T to the 5th at 5 gigahertz, which is, of course, absolutely crazy. Nothing really does T to the 5th, right, except for something very exciting, you like to think. So we ended up scrambling a bit of multi-frequency time so we could get some of these physical process or physical parameters for this TDE. So we could do things like estimate the date of the outflow. So the first thing I have to say is, so, when we have these SEDs, you get the radius, the energy, the magnetic field, the density. Those are the primary parameters we can extract. You do, however, have to make some sort of assumptions because, it is a point source. So what we did is for the volume, you can have 2 extremes. You can have a spherical outflow going in all directions, or you could have a jetted outflow of, we said 10 degrees. So something that you might have from, say, a gamma ray burst type jet. And then once we had that, we could have our various radii, and then you could extrapolate backwards to see where exactly the disruption came from. I love this plot, by the way, because I show this plot to high school students and they understand it. So it's like, okay, it's very obvious, like, okay, you have a velocity. The velocity we have, if you have a spherical outflow, is about beta of about 0.2. A jet, the maximum outflow would be a beta of 0.6. So something that's a mildly relativistic outflow, something we haven't really talked about before. And then the disruption date we find is about 750 days post-disruption from the initial TDE event. We can then also plot this onto the parameter space of, so this is velocity here on the x-axis, this is energy here. These are the previous TDEs in the literature, some of the radio TDEs. And then you could say this is Swift J1644 plus 57. By the way, this is the most recent observation. It became non-relativistic over time, of course. And you can see that AT 2018 HYZ is definitely living in a very unusual parameter space, kind of in the between the non-relativistic and the relativistic populations. So something very interesting is happening there. The other thing you could ask me, though, is, okay, like, what if it just turned on because suddenly there was a huge density region, that it was a low-density environment around the black hole, then you're going outward and you're hitting some sort of dense cavity. We don't really see that, though. So if we have here, this is radius on the x-axis, density on the y-axis. Here is, for reference, Sag star, and here is M87, and a few other radio TDs as well. AT 2018 HYZ is not a very high density environment around this black hole. There's nothing really showing an unusual density that would make you think, oh, maybe it was just turning on later because there was no density earlier. It appears to be something else is happening. So we argued that it was, at the time, a delayed outflow. But, you know, time progresses and, you know, you keep getting radio data. So I'm going to tell you guys a bit what AT 2018 HYZ has been up to since. So here's the plot I showed you guys earlier, and now I'm going to add the data since then. So this paper came out, it was mid-summer 2022. And this is the data we've collected since. So it's like, if you're doing like little bottle of wine bets, all I can say is you're going to lose every single time if you're betting against HYZ. It just keeps shooting for the moon every single time we check in. It's a few millijansky brighter. Which is really incredible. For the record, the last observation we had was in February of this year, and it was about 26 millijanskys. We started at 1.3 millijanskys. So this is very, very bright radio source. I'm going to just zoom in here so you can see a bit better what exactly is happening in this evolution. So this was, you know, when it was still T to the 5th. I think it's fair to say we're not at T to the 5th anymore, but it's still rising pretty fast. I think that I should also mention this is happening at every single frequency that we're looking at in our multi-wavelength frequencies. It is still rising. I'm not seeing any stop in its rise. The other thing that's crazy is it's kind of just the peak frequency. Okay, it will shimmer back and forth a little bit, stuff like that. But it's mainly just the SED is staying the same roughly for the peak frequency, and it's just the peak flux just keeps building on it. It's actually really incredible to see what is happening with this source. I will also segue briefly. So I have a slight detail that I should say. There was an erratum. Our paper came out after it was published. The VLA came out with a quirk in their, or a mistake in their pipeline that the L-band, S-band lowest frequency observations were affected by in that first paper, where basically the peak flux is slightly changed and then the peak frequency also shifts slightly. If you're one of the theorists who's been working on this object, please go. There's a Google Doc, which is also available at the QR code. It affected 3 observations in that original paper. We're working on erratum, but if everybody's already here, I think it's easier to just show this to you and encourage you to go get those data values. Anyway, to continue on, our next steps, though, are VLBI, because so I didn't get into it earlier. When we first took our data, we argued that AT 2018 HYZ was inconsistent with an off-axis jet. You know, we have our relativistic jets pointed straight at us. We should have more of them not pointed at us. We haven't seen this population. The reason we said at the time that it was inconsistent was that the emission started too late and it rose too quickly to be an off-axis jet based off some theoretical models. Of course, theorists are great because then, of course, they'll tell you, actually, this is very possible. And there's been several papers arguing that actually it's an off-axis jet with various parameters, various models out there. So, you know, the best way to do this is then to link together radio telescopes to try to resolve your source, which we can do in radio because, of course, we're very lucky people that our wavelengths are so long. And this is like our great advantage. So we use the VLBI, so you're linking telescopes all across the United States. We also threw in Effelsberg in Germany to get that really nice long baseline to try and resolve the outflow. So we have an observation from last year that was kind of marginal. You're not going to do it. Okay, you apply again. 1 year. All I'm going to say at this point is it's a very intriguing result. And maybe if people want to talk about it later, we can talk more about it. But VLBI is very finicky, so I don't really have results I want to show just yet from that. But it's been a very exciting new project. I think combined with the data that we have from the VLA, it's going to be very exciting to see how HYZ goes forward. I think it's also just incredible to see, as I said, it keeps getting brighter. It's still not stopping, you know, years after in its rise to dominance. I don't know. Anyway, so Looking ahead, though, so HYZ was just one very fascinating granted object from a survey about 24 TDEs. So I'm going to tell you guys a bit about the rest of the sample. So here we have days from detection again. This is the exact same plot. I just cut off Swift J1644 plus 57. You have DSG here, HYZ, Assassin 15OI, IPTF 60FNL, and I'm going to add the rest of the survey. So we actually had 10 new TDEs in this sample of 24 was ultimately the cutoff, what we ended up having, optically selected TDEs that had no radio emission at these earlier times in the first few months that are then detected at later times. So this is a huge percentage of the TDE population that we have just been completely overlooking. So this plot, by nature of being also just the first radio TDE sample that's been published, is a little complicated. So I'm going to just point out a few things in this plot that absolutely fascinate me. The first one here, for example, so this is a source called Assassin 14AE. You have very good limits, and then it's about 2,000 days after that it started rising in radio. About T to the 4th, it's been rising. We have other observations that are, after this paper went out to the archive, and it's still rising, I can tell you right now in radio, at roughly the same rate. So that's just a very fascinating mystery to me. There's several here, unfortunately, because nobody was really expecting this emission. Our sampling is not really what we'd like. So like, there's these peaks here that when they were first discovered were consistent with, Assassin 15OI or HYZ, but have been fading since we discovered them. So what exactly is happening? That's not very clear. We do have some second rebrightening. So AT 2018 DSG actually rose and then faded. We have a few others right now that are not yet published. So it's been very exciting to see what exactly is happening with these second brightenings that Adele was alluding to in one source. It does appear to also happen where if you have radio emission at early times, you can have significant second brightenings in your TDE population. So that's really cool. Another way to think of this, so if we just do a histogram here, so this is first radio detection on the x-axis and just number of TDEs. This is just everything I could find in the literature for radio TDEs to date. And you start seeing, okay, there's this group here. Oh, sorry, I should mention the dashed lines are where you had a first observation after the optical detection, and then the blue filled is when you actually have a radio detection. So the first ones here, this is primarily the jetted TDE, so your very energetic Swift J1644, AT 2022 CMC, those guys you can detect very quickly. You have this bulk of the population that's like, or sorry, a small bulk of the population, which is the traditional radio TDEs, I suppose we could call it, where you have them at 100-ish days, maybe, where you're first going to get them detected. But the majority of them really are, hundreds or even thousands of days later that you're seeing the radio emission. To be fair, just because of the sampling that is in the record to date, because we were not following these TDEs, there's a very good chance that this gap is going to fill in over time. I'm not arguing right now that there's really something intrinsically different about the early TDEs and the late TDEs. I think it's very likely that we'll find there'll be a spectrum. But right now, it's just kind of a bit of a puzzle for what exactly is going on here and what this is going to look like. Another way we can think about this is if we look at peak radio emission. So days post optical discovery, whenever you have your peak, you can always just, of course, put something on if you have a second peak. And what we see, once again, is the majority of these TDEs, you'll have the peak of the radio emission actually closer to 1,000 days than in the first couple hundred days. A lot of them are also just still rising. We don't yet know where exactly they're going to end up on this histogram distribution. So that's also very exciting. I think this is a time scale, like the VLA large program, for example, in radio, when it was designed, we were not planning on time scales that were this delayed. So it's really cool. So we have SEDs for most of these, so then we can start extracting the physical parameters. So I'm going to talk about those briefly. First of all, it's not so easy if you're just like, okay, I'm going to take my radius values, extrapolate backwards, and try to figure out, so some of these you can get a rough date for the estimated outflow. It's consistent with the upper limit, so similar to what I showed you for HYZ. A lot of these, though, it really does not work. I'm hoping that as we keep studying these outflows, maybe this will become more clear. Some of these will, you have a bit of scatter because the p-values change. Probably something to do with inhomogeneities and the outflows, something like that. So hopefully this will get better over time as we keep monitoring these sources. But right now, there's a lot of just kind of best estimates you have to make for estimated launch. So for example, the last upper limit that you have, you can use as a starting point for when the outflow might have started. Yeah, so the data is not straightforward, and you do have to make some assumptions. But you know, we can go back to that earlier plot that I showed you earlier. So this is velocity here, this is energy, and this is with all the new radio TDEs and everything in the literature. For simplicity, I'm only plotting the highest energy SED point that we have on this plot. Also, some of these they have a lower limit with an arrow pointing in a direction. That's because the VLA only goes to 1 gigahertz, and for a lot of these TDEs, or even if you go to 800 megahertz with Meerkat, which we did, the peak can be lower. So then if you can't constrain the peak, then you unfortunately have a lower limit. So we're just using those to be conservative. But you can see the point of this plot is most of this population is living down here in this non-relativistic regime. This is for like where 1BC supernovae live, for example. They definitely are not up in this jetted region for the most part, which actually makes sense, right? Because like if these were all, say, off-axis jets, okay, HYZ might be an off-axis jet. It could live up there. But that would be very confusing, I think, for the rates that we're seeing in things like optical, like if these were all off-axis jets, that just doesn't really make much sense in terms of what we're seeing. It makes more sense that we have just a delayed outflow of these radio things that are also non-relativistic. We can also look at the density, because once again, you can say why maybe we just have these, you know, walls of cavities around supermassive black holes. Once again, does not appear to be the case. So in this plot, this is the same plot, just I'm adding all the densities that we have here for these various TDEs. Once again, there's nothing really outstanding surrounding these supermassive black holes. They all appear to be pretty low density environments. So that's been pretty cool. I'm going to touch briefly here on multi-wavelength observations and multi-wavelength clues that we might get. So Kate Alexander is currently working on this paper, which will hopefully be out soon. And it's basically the X-ray and optical data for all these TDEs that we've been studying and what I've showed you. So we can use the optical and UV light curves to basically model the accretion rate of these TDEs using MOSFET in order to see what is going on. You can compare that to the radio onset time. So there are some assumptions, of course, baked into MOSFET, but this was a first try to see if there's anything interesting. This here on the right is AT 2018 HYZ. So here you can see this is the radio data. You can see over here is where the radio light curve turns on. And then the question here was, you know, could AT 2018 HYZ's outflow be launched by an accretion flow state change? The timing roughly aligns with transition expected at a few percent Eddington or maybe super Eddington phase if the disk formation is delayed relative to MOSFET. So maybe. We should note, though, the radio rise is not accompanied by any dramatic X-ray rise in AT 2018 HYZ. There's been about a factor of 2 change since its initial discovery in X-rays. That's not really a smoking gun for anything related to X-ray type models. I should also note, side note, for AT 2018 HYZ, I can't begin to describe what a garden variety TDE it was when it was discovered, which is also very interesting. There was nothing at the time that would make you think that this is a TDE that's going to suddenly start shooting for the moon in this. And I mean, it's going to be a pretty cool paper once we see it. If anybody has specific questions, I'm going to direct you to Kate on this. If you have a question about any TDEs, because some of them are, you know, they do this, some of them do that. There's no immediate correlation across the entire population. I think I can say that much for this point. So yeah, just some final thoughts. AT 2018 HYZ is the first TDE with a delayed, mildly relativistic outflow or an off-axis jet. Could be, we'll see. It's still rising at all frequencies at about 2,000 days post-disruption. We have VLBI data. Hopefully it will be able to share that with everybody soon. And otherwise, yeah, delayed outflows in TDEs are ubiquitous. I think that's pretty clear. It's about 40% of the population is showing this sort of trend. And we don't really understand what's going on yet. So stay tuned. I would love to hear everybody's thoughts on this. And thank you very much.
All right. Thanks, Yvette, for the great talk. Let's see, looks like Paz has a question.
Thanks, very interesting talk. I appreciate the presentation in a very agnostic way. And it's really more of a comment than a question, so excuse me for that. But I wanted to say that this rise, very fast rise that is seen in the radio, is something very natural for forward shock synchrotron viewed far off axis. It's not something that requires changing what we know about the physics. T to the fifth, even T to the sixth, you can get even more. I will talk about it later in the meeting. And the other point that I want to mention is that using the equipartition values for the radius, for the velocity, for the energy, can be very misleading, particularly for the energy, but even for quantities like the radius. Once we're talking about potentially an off-axis event, we could be off by a large amount. So saying that a specific event is relativistic or not relativistic we always need to have this asterisk. There is the possibility that if it's off-axis, our estimates could be completely off, and for the energy, even on-axis, the energy could be much higher than the equipartition value. It's very much a minimum on the true energy.
No, for sure, for sure. And I know there's been some great models that have been published on AT 2018 and HYZ in particular. I will say, to be clear, like, I'm very agnostic right now about what the ultimate interpretation is going to be for HYZ, just because it's like, every time if you check in every couple months and it's 3 millijanskis brighter, like eventually you're like, this is not a normal TDE. And you could see it even with the rest of the sample. It's clearly an outlier in what we have going on at these times. So,
thank you.
Looks like Brian has a question.
I guess to push back in a comment, but then also to have a question. So my pushback is just we have seen off-axis jet, the neutron star merger, and it did not rise as quickly because the jet has structure. And so I think that one constraint on off-axis models is you need a very core concentrated jet, and I think we had evidence that wasn't the case in J1644. But that aside, my question is, with VLBI, are we able to actually distinguish an off-axis relativistic jet from a collimated, mildly relativistic disk wind? I mean, in the sense that, probably there's an inclination angle dependence to how, the size of this on the sky. So if we do resolve it into, say, 2 lobes, how do we know that that's an off-axis jet and not just a fairly fast disk wind, maybe viewed more edge on?
Yeah, I mean, that's a good question. I guess a lot of what you can do is because you're also just going to have the centroid move, so you are going to have some velocity associated with it, is going to be the ultimate dream here. So
the idea would be if you see proper motion at C.
Yeah, so we're basically hoping to see the proper motion changing. So yeah, we have this observation now. We have another observation coming up in another 6 months. So hopefully this is going to be enough to see the proper motion as well.
So it's not the physical offset. Okay. Thank you.
Wyndon?
Yeah, so there is the alternative to the off-axis jet case. There is a delayed outflow case where they have a disk state transition, and that occurs at percent of Eddington. So you can easily have an upper limit on how much energy there is. It's a percent of Eddington, and then lasts for maybe several hundred days. And is that energy enough to actually accommodate for the minimum energy from the equipartition 10 to 50 ergs?
I haven't really thought about that, to be honest. What do you think, Kate? Maybe?
Yeah, no, it's a good question. I think, the plot I showed is definitely intended to incite some discussion. So I'm around and I'm happy to chat more about possible other models. This is just one possible model. And also, if it's an off-axis jet, then maybe the launch time could be earlier than the red line that I've shown here, in which case maybe it's associated with the super Eddington accretion as opposed to the delayed accretion. But I think it could be either. Right now, I think we are still exploring various theoretical models, so there's a lot that could be done. But yeah, it would be interesting to look more systematically at the sample and figure out if there's anything we can set from the energies required.
So this peak that you see, like the rebrightening, seems to be occurring almost always about 3 years later, something like that. How does this quantity relates to other typical timescales of tidal disruption events?
So like timescales in terms of how we see the brightening happening for or in radio for?
More like other timescales that you expect, I don't know.
Yeah, I mean, years is a very strange timescale, to be clear. Yeah, so I mean, it's a couple years. Some of them are several years, like Assassin 14 AE is something like 7 years after. And so, you know, there's also still a decent percentage that haven't turned on that we've been following up in every year since. 1 or 2 of those since have turned on. The rest of them we're waiting. So, okay, right now it's 2 to 3 years. That's probably somewhat because, okay, ZTF was finding a lot of TDEs at that time, blah, blah, blah. So, you know, we are still affected by these systematics. But what the overall distribution is going to be is, you know, we'll see.
So it's basically related more to your
I suspect it probably has to do with the observational constraints over a phenomenological thing, yeah.
Thanks.
All right, I'd like to encourage if there's any students in the room who have some questions. You know, don't be shy. If there's anyone who wants to ask a question about anything they've heard, yeah.
Hi, I'm one of those shy students. I have a quick question about the off-axis jet interpretation. Other than VLBI, is there any other smoking gun that would be, you know, a red herring to it actually being an off-axis jet?
Smoking gun is hard. That's why we're having this debate, right, on the interpretation. I mean, the ultimate trick, the problem with a lot of these off-axis jets, you have to make some sort of assumption on what the degree angle is of the jet, as I think you know. And then it becomes a bit difficult if you have this free parameter that's quite a big free parameter. Yeah, so that's still a bit of a question in terms of that. Hopefully, though, with VLBI, you can also break that degeneracy and then have some estimate on the angle. So, yeah.
Thanks, great question. So I have a fun question for you, which is, what do you think is going to end up being the maximum luminosity for 2018 HYZ?
I think it's going to get higher than Swift J1644, like at this time. I think that's pretty clear if you look at the plot. Otherwise, you know, I think we can have another bottle of wine before I go further in my estimates. But yeah, like, I know there's some models that say it's going to start sharply turning right now, for example. There was a paper saying this, and I just don't see that as happening. Like, you know, we could always be wrong, but that's part of the reason this is so fun. It's just going to keep rising until it doesn't. So,
all right. And I see one more quick question in the back.
Again, about the multi-wavelength clues that you may find. Something that we noticed also when studying 22 CNC, it was well observed in the optical as well as previous TDEs that also had optical light curves. We noticed a bit of a pattern, which is that they tend to be very overluminous and featureless TDEs. So this could be, you know, not the smoking gun you're looking for, but maybe an indication. Could you expand a bit on whether this may have been revealed by previous observations in the optical?
Yeah, that's a great question. And that is one of the things we looked at, if there's any correlation between peak optical luminosity and peak radioluminosity. And I think right now we're still a bit limited by the limited sampling for the TDEs that exist in the literature. I mean, as Yvette mentioned, some of these TDEs have not yet even peaked in the radio. So we did sort of look to see if there was a correlation. There wasn't anything super obvious. But I think that before saying anything definitive on that, we really need a larger sample that has good multi-wavelength coverage at both early times and late times. So now that we know this is a thing, we're definitely going to work on getting that for future events. But yeah, very, very good question. So I think we will, I think we have to move on to our final speaker. So let's thank Yvette again.